Section 4.3, acceleration! That's what comes next. So we're looking at average acceleration and instantaneous acceleration. So our average acceleration is going to be our same basic definition once again, change in velocity divided by the time interval. Once again, the only difference is now we have little arrows on top because these are now vectors and we can handle more than a single direction at once. That's great. It's much more interesting to work with more than just a single one-dimensional problem. Instantaneous acceleration is again looking at the limit of our average acceleration as the time interval approaches 0. And so this then becomes a derivative, that the acceleration is the derivative of velocity with respect to time. So in unit vector form, we can once again write this as the derivative of all of the x, y, and z components of velocity, or that the acceleration is dvx dt, dvy dt, dvz dt. So another way we could say that is that the acceleration can be written in terms of its x component, its y component, and its z component, where it's understood that each of those components is just the derivative of the velocity vector in that particular direction. This is a nice compact notation, so it's a handy one to keep in mind. All right, so note, as with velocity, an acceleration vector does not point from one point to another. It just shows the direction magnitude of the acceleration at that instant. So if we go back to our bead on the hoop, right, the bead is not pointing to, say, over here where it's about to go, unless you're looking at displacement. The velocity we saw was tangent to it. It was going off at this angle. And the acceleration is pointed in an entirely different direction. It's pointed down and to the right, showing that the bead is changing its velocity in this direction. So you can again break it down to the x and y components, but this shows how the velocity is changing as time passes. Alrighty, so let's try this out. The checkpoint. So here are 4 descriptions of the position in meters of a puck as it moves in an xy plane. Look at each of the expressions and determine, are the x and y acceleration components constant? And is the acceleration A constant? So there's 4 different ones. I want you to look through each of them, come up with an answer to all 3 of those questions for all 4 of the scenarios. So go ahead and pause to do that. Alrighty, hoping you did that. So as we take a look at this, we'll start with the first one, right? It mentions x is equal to -3t squared minus 4t. Well, if we want to know if the acceleration component is constant, we can calculate that, right? We know that the acceleration component in the x direction is just the derivative of the velocity in the x direction. And we know the velocity in the x direction is just the derivative of the position in the x direction. We could write this as d dt of dx dt. In other words, all that we have to do here to get the acceleration is take the second derivative with respect to time of the position for each of the directions and see how it compares. So if we look at this first one here, we get with the first derivative, d of x or dx dt, we would get that it is -6t, right, plus 4. And then if we take the second derivative, which is going to be the acceleration, then that's just going to be -6. We need to know, is that constant as time passes? Well, the only way it's not constant with time passes is if there's still a t in there. Since there's no time dependence, then this is constant. So that is a yes. Right? We could double check for the y direction too. Right, this is a yes, so it doesn't just look like y. And if we take the second derivative of that, if we take the first derivative, we would get 12t. And the second derivative, minus 4. Second derivative would then be 12. for our a sub y. So that is looking good too. No time dependence, so also entirely valid, right? Now what about for case 2? For case 2, notice the time is now cubed. So if we take the first derivative, we'd be okay thus far. We'd have, let's see, negative 9t squared and minus 4. But then when we take the second derivative to get to acceleration, we now have negative 18 times time. We now have time dependence, right? This is a problem. If there is time dependence, then it is not constant. Right? It is changing as time passes. Right. So that's the basic idea. You can double check it with 3 and 4. What you'll notice is that with the y, by the way, sorry, I should finish this one. With the y, because it's raised to the second power, it will check out as being constant. So that one's okay. You'll see with number 3 that because it's raised to the second power, the second derivative will be constant as time passes. But for number 4, the x component is raised to the third power. So that is not constant, even while the y component is constant with time. But if any one of the components is not constant, then the overall acceleration will not be constant for it. So hopefully that helps to highlight the ideas of how you can differentiate to see how the position will change and influence the velocity and the acceleration as time passes. Note 3 and 4 are just a different notation. So they're written in unit vector notation, where 1 and 2 are written in terms of the scalar components. And either one is entirely valid here. So there we go. We've now seen our position and displacement, our velocity, and our acceleration all redefined in 2 and 3 dimensions.